Good afternoon, or actually good morning. Sorry I can't be there in class with you guys today, but as you get this on DVD, I am in Long Beach, California at the Soil Science Society of America annual meeting. Where it might seem like a vacation, it's still quite a bit of work, but it's quite enjoyable. At any rate, I get to deliver this to you, and I promised you'd see me this week. I just didn't say you'd see me in person. So today we're picking up where we left off with our last lecture. And we are just in the middle of soil temperature, and now we complete that today. So just an announcement. Of course, this week is a lab break, so you should utilize this time wisely. We have lots of things due in the next few weeks, and a lot of things to do. So it's time to bone up on studying and really utilize this time. So where we were, we talked about wetlands. We defined hydric soils. We talked about moisture regimes. And then we got into soil temperature, and we defined soil temperature. We talked about the factors that influence it, and we kind of just left off talking about thermal properties of soil as we got into what influences soil temperature. And that's where we pick up. So we started with this idea of energy, and we talked about the heat of vaporization. And we defined the heat of vaporization as the amount of energy required to vaporize water. A pretty simple definition, water going from the liquid to the vapor state, but it turns out that takes an awful lot of energy. Okay? And how much? And we said that was about 540 kcals per kilogram, or in the SI unit, 2.25 megajoules per kilogram. So quite a bit of energy when you think about the difference between that and the specific heat, the amount of energy required just to raise the temperature of water 1 degree. Is quite a bit of difference. And so this heat of vaporization can be a tremendous input of energy. Now we have these physical properties, and now we can go a little further and talk about the transfer of heat in soil. And just like we talked about the transfer of water in Darcy's law, we talk about the transfer of heat in kind of a similar fashion. And there's an equation to express this, and it looks like this. It's the quantity of heat is equal to K dt with respect to x. So we define this, the quantity of heat transferred across the unit cross-section. And usually we're talking about something perpendicular, this perpendicular transfer. And you've heard this as flux, and technically this is called thermal flux. Okay? And it occurs in a unit area and a unit area of time. And that key to that is the temperature difference. So the greater the temperature difference, that dt, the difference between the temperature at the two ends, the greater the transfer. And this is expressed here as T1 minus T2, this temperature gradient, over some distance x. And now we have that wonderful factor K. We've had K for conductivity, and now we're looking at thermal conductivity. We've already looked at K in terms of water flux, in terms of Ksat and K unsat. And now we have the same idea, this expression, this number that expresses the rate of heat transfer. And so we think about what influences that rate of transfer of energy and heat. And the first thing is soil moisture. I put soil moisture here in capital letters because soil moisture is a very, very good conductor of heat. It's much better, and the opposite of that is air. So if you have pores that are filled with water, the conduction of heat, the transfer of heat is very efficient and very rapid. If you have those filled with air, of course it's not. And of course that's why we insulate our houses. We have air pockets, and that eliminates the rapid movement of heat, the transfer of heat across two distances. Okay. So then when we think about soil moisture, now we move to the dry soil, and we'll look at organic matter content. So what does organic matter do? So we talked about organic matter had a very low density and a very high pore space, and also increased structure stability. So because of this, when we think about organic matter in a dry soil, the rate of heat transfer is greatly reduced by increasing organic matter. Essentially, you create more airspace. Again, if we make that a wet soil and bring soil moisture overrides that. So in a dry soil, the rate of heat transfer is reduced by increasing organic matter content. And that should be fairly easy to follow. We've talked a lot about physical properties, total pore space, and so this just follows up on our discussion of physical properties and total pore space. Soil texture. And just as soil texture was related to total pore space, and we get back to the same idea of air, the more total pore space, the lower the rate of heat transfer. Greater insulating properties. Again, soil moisture makes all of these things kind of irrelevant because soil moisture is very high conductive for heat. And then bulk density. And so increased bulk density, what would you expect? So if you increase bulk density, what happens to total pore space? It goes down. Okay? So if you decrease the total pore space in a dry soil, you should increase the rate of thermal conductivity. So all these things, think about how much air-filled pore space is in the soil, and it's directly related to that. Put in soil moisture, and the rate of heat transfer is very large. Take it away, and then we can think about these other isolated factors. So that's probably a pretty reasonable way to think about it. There's a nice illustration of this concept, and it's illustrated in the book on this figure 731. And this shows some low K and loose and dry soils, and you see there's a lot of airspace illustrated. You compact that same soil, reduce the airspace, and it increases the K, the thermal conductivity. Then you put in water, and it increases it further. So this really illustrates that important aspect of airspace. Air is an insulator, and to the extent that you can reduce the airspace, increase the contact between the particles or among particles, you increase thermal conductivity. That should be intuitively pleasing to think about. It kind of makes sense. Now we'll move along with soil temperature and root growth. And we've had this idea of some kind of minimum soil temperature, biological zero. We expressed that at the beginning. And now we'll take that a little further and look about ranges, low, optimum, and reduced growth rate. So pretty much the minimal range for temperature where you actually have any root growth at all, somewhere between 0 and 7. So that range, 0 to 7, that covers our 5 degrees C, that one number we use to express as biological zero. And that average, 5 degrees C, is a pretty solid number. And here it just illustrates there's a range. Okay? So sometimes we'll talk about the range, sometimes the number, but we're still talking pretty much about the same thing, minimal activity in terms of growth. The optimal range, somewhere around 10 to 25 C. Okay? And that gives us the best root growth. So we're talking about soil temperature in the 10 to 25 C as being fairly productive. And of course, this varies by species, but in general, over a wide number of species, this optimal range works. Now, what happens when you get above that? So above that, you start to have increased respiration, you start to denature enzymes, and things go south, so to speak, very quickly. And so very high temperatures are damaging. So the maximum range, 25 to 35, once you get beyond this maximum range, things drop off dramatically, and there can be mortality. Now I have a graphic to kind of illustrate this. It's one piece of data out of a Canadian study that kind of supports these ranges. And there was some work with Norway spruce seedlings and soil temperature by Farndon, and this was a Canadian publication, and it follows along pretty well. We see the minimal in the 0 to 5, then the optimum in the 10 to 25 range, and then you don't see anything measured beyond 35 because we start to induce mortality. So these data kind of illustrate what's going on. It's just one more illustration to fill in some of those abstract ideas or in support of those generalizations. And for Norway spruce. And I could have picked any number of these studies from the literature. In fact, those numbers are drawn from the literature of these fairly wide literature reviews that collect data from all over a wide variety of species and a wide variety of places. So onwards, soil temperature. So sometimes soil temperature can be a little high, and we think too much of a good thing. So what are the instances where soil temperature might be damaging, excessive soil temperature? Well, you look in some of the drier and warmer regions, look in the south aspects and dry soils in the western United States, and where we have limited rainfall. Sometimes with those aspects, remember those southwestern aspects have greater incidence of energy and have greater temperatures, sometimes they can actually lead to mortality. And on top of that, where areas where they regenerate, a lot of times in Douglas fir and some of those other species, they'll regenerate and use a prescribed burn to eliminate the competing vegetation, and that leaves a black surface. So with the increase in black surface, kind of increasing the energy absorption, coupled with this effective slope, you can actually have a very high temperature that might be lethal to seedlings. And in some extreme cases, they've actually built these little shade houses, little kind of A-frames to put over seedlings to protect them from the direct radiation. And those are extreme sites, and those are difficult to plant. But excessive soil temperature in those cases, somewhat problematic. It's not only too much, but there's also too little. Another aspect of this is the whole process of reforestation, developing seeds, growing the seedlings, and bringing those seedlings to the field, and then planting, is quite complex. And there are numerous places in there where the process can break down, and that is in seedling handling. So if you don't keep the seedlings moist, you let them expose them to sunlight and expose them to wind before you even start, you have a problem. And there's no sense planting dead seedlings. It's expensive in more ways than one. So seedling handling in this whole process of reforestation and planting is pretty critical, and there's been a lot of work devoted to this. There's less of that now, less artificial regeneration, but in past years, artificial regeneration was quite large. And you could take a look at, as an example, look at all the plantations in New York State that were put in the 30s and 40s. Seedling handling then was a pretty big issue. And then we get down to the temperature not enough or too cold. Okay? And so where do we have low soil temperature? So low soil temperatures tend to occur at the higher elevations, right, and the northern latitudes. So here we have the opposite problem of a very limited window sometimes to take advantage of the soil temperatures that are favorable to growth. Okay. And the same thing, even in these cool conditions, seedlings can be mishandled. Desiccation occurs very rapidly. And so it's very important transporting seedlings to keep them covered and keep them moist. And that's just some standard procedures for nursery management. We used to teach courses in nursery management in 10, 20, 30 years ago, and not so much anymore. There's still a few around in artificial regeneration. It's simply not as common as it used to be. But there's still people that do that. And to illustrate that point, there's some data from British Columbia, okay, and it shows the window of planting. And you see it's very narrow. Okay, we have the first thing that happens in the spring is you get bud break. And so in these northern climes, this happens fairly late, and then root growth starts before bud break. So as the initial period of root growth, let me illustrate that on the screen, the initial period of root growth here takes off, and as that goes down, then shoot growth begins. Then shoots elongate. As that slows down, okay, buds elongate. So the window for planting is right here when the soil is warmed up enough to allow for increased growth. So that window of planting just occurs between maximum diameter growth and lets off as diameter growth drops in root growth. So this is a very narrow window, particularly in northern climates. So it takes some planning to take advantage of the appropriate air temperature and the appropriate soil temperature to ensure successful regeneration. Pretty interesting problem when you're trying to reforest or establish plantations up in the northern climates. Of course, here in the central New York, that's not a huge issue. We have a pretty nice growing season. Anybody recognize this? This is actually a picture out of the book. It's pretty interesting. So here we have these fence posts, and they're set in these concrete pieces, and they've been pushed out of the ground. So what you're looking at here is a picture of the result of frost heaving. So frost heaving, the shifting of ground that actually pushes rocks and breaks plant roots and so forth out of the ground. So we ask the question, why does this occur and how can we prevent it? Well, it's not only bad for fences, it's bad for seedlings. Here's a picture from the Saratoga nursery. These are fairly coarse textured soils. But when you have spent all this money to establish seedlings and then they're all heaved out of the ground, it's a little disheartening. So that represents quite a waste of resources, also the waste of a growing season. So frost heaving is an interesting issue, and it bears a little bit of discussion. And so we'll spend a few minutes talking about what it is and how it occurs. As a close-up. Actually, if you take the Advanced Forest Soils course next semester at 40535, we actually have a trip to the Saratoga nursery and talk about nursery production, and among other things. It's kind of a neat trip. That's my commercial. So we get down to the frost heaving and try to define it and talk about it. So frost heaving results from ice expansion. And so segregated ice lenses expand, and when they expand, they increase the volume. And this occurs as you go from liquid to solid, freezing. It's just the ice is more volume than water. Okay, so these segregated ice lenses are responsible for lifting all of these even fence posts out of the ground. So how do these form? There are three risk factors that contribute to frost heaving, the development of these ice lenses and continued heaving. And the first, of course, sub-freezing temperature. It has to be a long enough period of sub-freezing temperature. And so without freezing, you can't have any frost heaving. So that's the obvious one. It's like the oh-da, an oh-da moment. So beyond that, there are certain soils that are most susceptible, and these are fine-grained. And the biggest is silt. Okay, so silt, as we will soon find out, has very little cohesion. So silty soils are the most susceptible. Some clays. Now clays, we're going to talk about clays and how they vary in terms of structure. So there are some clays that are susceptible and some that are not. But silts, by and large, always susceptible, and some clays. Now, the text talks about silty soils. There are some publications that talk about expansive soils in Russia that will be subject to frost heaving. But silts is uniformly agreed upon. Clays, sometimes yes, sometimes no. So the fine-grained soils, these are most susceptible. This is where water is able to be transported. And finally, there must be a source of water. So these are continually heaving, so in order to have that process continue, there needs to be a continuous source of water. So with those three risk factors together, they lead us to the potential for this frost heaving, this bad result. So the text has a nice illustration in figure 725, and starts out, so the soil freezes, okay, it freezes from the top down, okay, and their segregated ice lenses form, and they continue to form. Okay. And so as they form from the top down, because of course the surface is frozen at the top, they lift and break. And so they actually pull roots apart and lift rocks up, and fence posts and so forth, and that's illustrated here. And as that water is continually to be supplied, those lenses aggregate and continue to grow, those isolated lenses. We have just a continuing problem, and the heaving becomes worse. Now this melts from the top down, okay, and when it melts, the soil subsides. Of course, the roots don't go back to where they were, and everything remains where they are put. And so that log here, this fence post that's jacked up, remains jacked up. This comes down, the soil subsides, and next thing you know, you have rocks and so forth closer to the surface, and broken plants and heaved fence posts. And that's a pretty good illustration of the process. The interesting thing is, thermodynamically, it makes a lot of sense why this occurs. So freezing water provides ice, and ice actually attracts more water to be frozen to it. So we talk about this, a sink for water. Water is attracted to the freezing front of ice. And we think about, we've already studied water movement in response to a gradient. And it was pretty easy when we were talking about liquid water to talk about potentials. And now we talk about a thermal gradient and a potential gradient. So let's consider this freezing front. So at the freezing front, the ice is cold, the soil is warm. So there's a thermal gradient. The water moves from warm to cold. So water is attracted or moves toward the freezing ice front, okay, that thermal gradient. And that contributes to this continual production of these lenses, and they continue to freeze and grow. The second thing is an osmotic gradient. So what happens when you freeze water? Salts are excluded. So at the edge of that ice, the salts are excluded, the ice freezes, and that creates an osmotic gradient. So you're concentrating salts at the edge of this ice, this freezing zone, and that's high concentration of salt. So there's an osmotic gradient for water to flow from the high potential, where there's low salt, to low potential, where there's high salt. So basically flowing towards the salt. And this is right there at the freezing front. So this adds to our gradient. We have a thermal gradient and an osmotic gradient, both acting in the same direction, toward the freezing ice front. And finally, there's a moisture gradient. And we already have this potential from high moisture content to low moisture content. So ice is actually desiccating, right? So you're freezing something, you're actually desiccating the system. You're converting that water to ice. The moisture content below that ice zone is higher, so you have this gradient in moisture from high to low concentration. So all three of these gradients working together in the same direction to move water from the soil to the freezing ice front. A thermal, an osmotic, and a moisture gradient, all working together. That's illustrated in this picture here. This is actually out of Giles Marion's, one of his publications from the Cold Research Institute. And here's illustrating soil surface. Here's frozen soil, and here's the frozen fringe. So we're looking at this frozen fringe, and so this is the freezing front. So at the freezing front, there's a higher osmotic gradient. So the chemical potential of water is lower. We go from low potential to high potential. That's illustrated on this graph on the left. And so that illustrates the gradient in osmotic potential. We have unfrozen soil and the water table. So the high concentration of water table here, the water table, lower concentration here. Here's the moisture gradient, high concentration to low concentration. Okay. And finally, the thermal gradient. This is cold, this is warm. And so these three gradients all contributing to move water towards the freezing front. Well, that kind of wraps up temperature. So we've been through the properties of soil temperature. We've looked at the factors that influence it. We've looked at the individual soil properties, thermal properties, and then we kind of close with an application of that in terms of frost heaving. So that is pretty much all we'll talk about for soil temperature. We even looked at the thermal conductivity gradient. And that brings us into our next, probably the most difficult for some, the most challenging portion of the course on the chemistry. But I think that's the first time I understood chemistry was when I took soils, and it made a little sense. So I'm hoping that most of you see it that way. So now we begin talking about colloids, those little things. So the context, and we have a little bit of the context already when we talked about soil physical properties, and just by way of review, they are small, right? So colloids, we talked about clays. What's the size of clay particles? What's the diameter? Less than 0.002 millimeters, 2 microns, okay? And that's small. Colloids, the colloidal portion of that, less than 0.001 millimeter. When you get less than 0.001 millimeter, that's colloidal, okay? Or 1 micron. And we talked about the effect of the small size. They had a high specific surface. Now we're going to talk about internal and external surface area. So we're going to make one more distinction, and that'll become clear. But just in terms of the external surface area, for the small size, there's a tremendous amount of it. But as we go on, we'll look and we'll explore internal surface area, and it dwarfs the external surface area. So here is our cube. We already used this illustration. We take this 6 centimeter cube. They're 1 by 1 by 1. It has 6 centimeters per 1 cubic centimeter. So this is 1 by 1 by 1. There are 6 sides, and it has 6 centimeter squares. That's the specific surface, 6 centimeter squares per cubic centimeter. So we divide that in half, and we go to 8. We divide that in half, we go to 12, and this goes up geometrically. So we already illustrated that, is that the specific surface, the amount of surface area per unit volume, is very high for these colloids. So just colloids, in terms of just this external surface area, just on these external surfaces, we have 1,000 times the colloid, the surface area of sand. Okay, so 1,000 times, and that's just the largest sand, the largest clay, and the smallest and small sand. Big difference, and it goes beyond that. It goes 10,000, 100,000. So this geometric progression is very, very rapid. So another thing about colloids, in terms of context, because of their size and their construction, they exhibit a net negative charge at the surface, and this illustrates it. And so when we talk about colloids, we talk about adsorbed cations. Okay, so this colloid here, represented by this square, at the surface expresses a net negative charge. So for now, you'll accept that, but in a few minutes, or in 30 minutes, we'll explain why. But for now, all these colloids exhibit a net negative charge at the surface. Because of this, positively charged ions, called cations, are attracted. And we call this adsorption. That's AD. I capitalize that, adsorption. Okay, so these positively charged cations are attracted and associated with these negatively charged surfaces. Now we refer to this system as a ionic double layer. The negative part of this double layer is the colloid surface. The positive are the cations. So that's the ionic double layer. These are adsorbed, attracted, electrostatic attraction. So what are the implications, this small size and this net negative charge and these adsorbed cations? Well, quite a few. Now we have something called cation exchange. And cation exchange is where adsorbed cations associated with the colloids exchange with cations in soil solution. So there's movement back and forth. You have soil solution, these colloids, so there's play back and forth. Some of these colloids, these cations are attracted to the surface and held, and they can be exchanged for other ones. Cation exchange. So let's think about the soil solution. Okay, so we have these colloids, and here's the soil solution. We have some H+, and of course this is a soup of cations and all kinds of things. I'm not showing any of the anions, but it's a veritable soup. And so from this soup I focus on a couple of hydrogens. Now it's possible under certain circumstances for these cations in solution that are loosely floating around in solution to exchange with those associated with the colloid. So here we have calcium, which is +2, and replaced by 2 hydrogen ions, and this is an exchange. And now calcium +2 is in solution, and the hydrogen ions are associated or adsorbed on the colloid. There's been an exchange. And again, I just showed 1 or 2, but this soil solution is it's a soup. It's a potpourri of all kinds of things, all kinds of solutes and ions. And we just picked out one to show this, simply illustrate the exchange of cation and soil solution with that associated with the colloid. That is cation exchange. So that has some more implications. We can measure the capacity of a soil to exchange cations. And so we define this as cation exchange capacity, CEC, cation exchange capacity. And the definition of that, it's the sum of exchangeable cations a soil can adsorb. Okay? Simply definition, the sum of exchangeable cations a soil can adsorb. These are exchangeable. They can exchange with solution to colloid, and we can measure how much that can occur. The measurement unit is centimoles of charge per kilogram. C for centa, mole, and C, charge. So centimoles of charge. Sometimes you'll see this written as C mole plus per kilogram of soil. This is the unit. It's the SI unit. Okay? And we'll become a little more familiar with that. Now we have to review chemistry. And what we have here is a mole. But it's not the kind of mole we're thinking of. It's one that might be easier to comprehend now, but now we have to think about the other kind of mole. Okay? And I always remember there was a cartoon when I was a kid, "Help me, Mr. Wizard." And so we're going to help you. Mr. Wizard's going to help you to comprehend a mole. Perhaps you never really got this down, or it was such a crazy abstract thing, but it's actually extremely useful. And so at this point, after this lecture, a mole should make sense, and it should be intuitively helpful to think about measuring these things in terms of mole of charge. So the mole, the definition of a mole, and we learned this in chemistry, Chemistry 1 or 101 or whatever your first chemistry course was, or perhaps even in high school. The mole is the weight of an element that contains 6.02 times 10 to the 23rd atoms. 6.02 times 10 to the 23rd. And that's burned in your mind, no doubt, from chemistry as Avogadro's number. Or a mole is referred to as the molecular weight. So very simple definition. So let me ask this. What is a centimole? And so centimole, C-mole, so you see this expression, C-mole. What is a centimole? So a centa, 10 to the minus 2, or 0.01. So 1 centimole, 1/100th of a mole, equals 0.01 moles. A centimole, that's simply dividing by 100, or multiplying times 10 to the minus 2. No problems yet. We move on. Well, why are we using charge? Well, we have a lot of elements, and they're all not monovalent. Monovalent, one valence. So calcium, for instance, is +2. It's divalent. Potassium, K+, is +1. It's monovalent. Aluminum, +3. Trivalent. Silica, +4. 4. So we would like to be able to make these reactions very simple and exchange them on a charge basis. Okay? So it's important for us to keep track of that charge. And the reason is that a mole of positive charge of X plus will replace 1 mole of positive charge of Y double plus, etc., etc. So all our comparisons of these reactions will be on a mole of charge basis, and it will make things a little simpler, a little easy to keep track of. And in the soil, the concentrations are fairly small. So we use centimole of charge, and this unit, a kilogram of soil. So typically, this is our ratio, centimole of charge per kilogram of soil. Now let's figure out how to calculate that. A mole is defined by the molecular weight, the atomic mass, the molecular weight, 1 mole. 1 mole is 6.02 times 10 to the 23rd atoms. All those different elements have different weights and masses for those 6.02 times 10 to the 23rd atoms. The charge is defined by the valence, +1 potassium, +2 calcium, +3 aluminum. These are charges that you'll become very familiar with, and you'll know them within a couple of weeks after we go through the lab. And so we come down to the mass of substance that provides 1 mole of charge. We calculate that as the molecular weight over the valence. And if you remember from chemistry, this is the definition of equivalent weight. So the molecular weight divided by the valence, the mass of a substance that produces 1 mole of charge, or the equivalent weight. Now this is useful because occasionally we have to convert mass to charge and vice versa. So we'll ask this question: what mass of calcium +2 provides 1 centimole of charge? Okay. What mass of calcium +2 provides 1 centimole of charge? So we're essentially asking, what is the equivalent weight of calcium? Okay. So the molecular weight divided by the valence is the equivalent weight. So for calcium, the molecular weight is 40. It's like 40.01, but 40 is close enough. The valence is 2, +2. So 1 mole of charge for calcium. How do we define that? Molecular weight over the valence, or 40 grams over 2. So for calcium, 20 grams of calcium will provide 1 mole of charge. That's the equivalent weight. 20 grams of calcium will provide 1 mole of charge. So far, nothing too difficult. Now, let's convert that to centimoles. Let's ask how many centimoles of charge that is. Okay. So 20 grams per mole of charge. To convert to centimoles, times 0.01 moles of charge per centimole of charge. Okay, so what's going to happen? Mole of charge is going to cancel out. Okay, and this simply comes out to be 0.01 times 20 equals 0.2. So 0.2 grams of calcium will provide 1 centimole of charge. So we've just converted mass to weight. So where did I get that? Here's a periodic table. So I looked for calcium on my periodic table. And there's calcium, and its molecular weight was 40.08, but we were just rounding to the nearest whole number. So I took that molecular weight divided by 2. I had 20 grams per mole of charge. I multiplied that times 0.01 for 0.20 grams per centimole of charge. So fairly straightforward. So you'll need that. Now the reason I went through that is you'll need that calculation in lab next week. And so this week is a lab break. This will allow us to catch up, and next week when we do chemistry, this is a very important calculation. So when you come to lab next week and for this, make sure you bring these notes and your calculator and of course your text, and it'll be much, much easier. And it'll be particularly easy if you actually read through the web material. So we're back to colloids. Now we have a way to convert mass to charge, and now we're going to look at the colloids in terms of groups or classification. So what are the major types? So organic. So organic, and we already know about organic matter, so they're pretty much consisting of carbon, hydrogen, and oxygen. Okay? Carbon, hydrogen, and oxygen. And there are these various complex molecules with these working groups. So these are organic colloids. Okay? C, H, and O. I have a humic acid model, and I'm not hooked up to the internet here, so I can't show it, but I'll twirl this and whirl this around when I get back, and I'll amaze you with the mouse. But for now, I'll just tell you that organic colloids are carbon, hydrogen, oxygen dominated, and I'll show you a model later. Okay. So the other colloids are mineral. Okay, so this is the major separation. We're already familiar with organic soils. Okay, we're just going to take that one more step and separate out organic colloids from mineral colloids. Now we have two different ways, two different colloid groups, and we have to talk about where does the net negative charge come from. So recall we said that each of these colloids expresses a net negative charge at the surface. And the mechanism is different for organic than the mineral colloids. And so I think I start with the organic ones actually. Okay. So where does this net negative charge? So this comes in organic colloids, it originates from the dissociation of hydrogen, H+. And there are three groups, and you'll need to know these. There's a carboxyl group, a phenyl hydroxy group, and an alcohol hydroxyl group. These are the three, so to speak, working ends of these organic molecules, these colloids. And we'll look at them individually. Okay. So here's an illustration of the carboxyl group. Now, if you've had any organic chemistry or biochemistry, you'll recognize this carboxyl group, the C double bond O, and the R. R represents some long-chain complex carbon compound, but here's the working end, this carboxyl group. This is the carboxyl group. So because of this double bond, it tends to be shared between these two oxygens. Hydrogen can dissociate. Okay? And under certain conditions, that hydrogen dissociates. So what happens when you remove H+ from this carboxyl group? There's a net negative charge expressed. Dissociation, move this hydrogen away, there's a net negative charge. And that's at the surface of this organic colloid, consisting of all kinds of these. Here's an illustration from Wikipedia showing the C double bond O. Here's the R, and here's the OH. And this dissociation here, as this moves away, leaves a net negative charge expressed here at the surface. Okay, the carboxyl group is one. The phenyl hydroxy group is another. So here's a phenol ring. Okay, it's the 6-carbon chain. It's circular, and there's double bonds, 3 double bonds, connect to oxygen to hydrogen. Because of these 3 double bonds shifting, shared here and here, hydrogen sometimes dissociates under certain conditions. So when this hydrogen, this H+ dissociates from this phenol hydroxy group, this leaves a net negative charge. The same is what happens when this H+ dissociates from the carboxyl group. 2 different groups, same result. Net negative charge expressed. And here's a picture of it. Here's a picture of the phenol ring and the dissociation. Pretty cool. Now we come to the alcohol hydroxyl group. So an OH, an alcohol, okay, on a hydroxyl group. So occasionally, under some circumstances, again, this H plus from this OH, this alcohol hydroxyl, can dissociate. And the same thing, when you remove this H plus and it dissociates, we have a net negative charge expressed here at the surface. 3 groups, same mechanism, okay, dissociation of H plus. Here's a nice illustration, a little picture of that in the stick molecule. And this H plus dissociates, and voila, net negative charge. So now let's put all those together. So here's a central unit of a colloid, okay, an illustration, a very complex molecule, but with the working ends. Here's a phenyl hydroxy group. Here's a carboxyl group, another phenyl hydroxy, carboxyl. And here's a net negative charge. There's no hydrogen there. Net negative charge here. So this calcium plus 2, this cation, is attracted or adsorbed to these 2 sites. It's attracted. This K plus, this cation, is attracted or adsorbed to this phenyl hydroxy dissociated hydrogen spot, and so on and so forth. So these cations are attracted or held by this net negative charge, electrostatic charge. This dissociation happens under low acidity or high pH. Now that is not apparent now. We'll talk about soil reaction and pH later on, and it'll come back and this will make perfect sense. But for now, just be aware that this is pH dependent, and as we get low acidity, that there's more dissociation of H plus and greater cation exchange capacity. Kind of neat. Again, adsorbed, not absorbed, adsorbed. This is a surface phenomena. These are attracted to the surface electrostatically, these cations. Adsorbed. Low pH, there's no dissociation. Okay? So this phenyl hydroxy group holds its hydrogen. This carboxyl group holds its hydrogen. Low pH, high acidity. And so this is pH dependent. This CEC, this capacity to exchange cations, depends, the sum of exchangeable cations depends on the pH. Okay, so let's move away from the organics. We had our organics, the hydroxyl alcohol group, the carboxyl group, the phenyl hydroxy group, and now we'll move to the mineral colloids. The mechanism for this is very, very different in terms of the source of the net negative charge. Okay. So, and there are a number of mineral colloids. So first let's look at the crystalline silicate clays. These are called the phyllosilicates, okay, for sheet, phyllo. Okay. Crystalline silicate clays. And one example, we're going to learn all of these, but one of them is kaolinite. So here's a picture out of the text, figure 8.3a. It's this crystalline clay, kaolinite, in these sheets, and this is a nice electron micrograph showing this beautiful arrangement of kaolinite sheets. A phyllosilicate. The second group are non-crystalline. Again, silicate clays, they have silicon aluminum, but they're non-crystalline. And sometimes we talk about amorphous or shapeless, but there's also something in between. There's some short-range order minerals. Okay? That is, they have a little bit of order, but they don't repeat in crystals. And they're still complex, but they exhibit some order when you look at some of the X-ray diffraction. So these things come from volcanic ash and some igneous rocks. And the general form, this Al2O3, silica and water. And we've already talked about these. Now we're putting them into this other classification, non-crystalline silica clays. We've talked about allophane and amogolite, okay, these materials that originate in volcanic ash and volcanic glass. And we refer to these when they're this partially, not quite amorphous, but not quite crystalline, somewhere in between. We refer to that as paracrystalline. Okay, paracrystalline. The important thing about these, allophane and amogolite, is that they have a very high phosphate absorbing capacity. So they just, and we call this phosphorus fixation. You put phosphorus on and they're immediately, the phosphorus is very highly attracted and doesn't move. Okay, and that's an important feature of these non-crystalline silicate clays of allophane and amogolite. Here's a picture of allophane. Got this off the web. It's kind of the hollow circular pieces. And this is the X-ray diffraction spectra. It shows that the peaks are rather complex and non-repeating. So instead of the nice regular peaks you can compare with some of the crystalline silicate clays, these are a little bit less well defined, and they're short order or short range, and they don't repeat. And this is a picture of immogolite, kind of tubular. It's the other one. Okay? And you see that this is referred to as paracrystalline. Okay, now we move to the third. So we've done the phyllosilicates, we've done the non-crystalline silicate clays, and now we move to iron and aluminum oxides and hydroxides. And some of these are crystalline, and some of these are amorphous. But this is the case where silica has been leached out of the profile, very highly weathered systems, very old, ancient, stable landscapes. Okay? And all that's left is iron, aluminum oxides, and hydroxides. Some of the examples, we've mentioned some of these already. Goethite, which gives the soil this brown color, that's Fe2O3 with water in the crystal, and ferrihydrite. And we've also talked about hematite. Okay? So we've mentioned hematite gives the soil these red colors. These are iron aluminum oxides. You see there's no silica there. Okay? And these in particular are iron. Gibbsite, the aluminum member of that, AlOH3, again, no silica. All the silica has been leached out. Very old, stable landscapes, highly weathered systems. I believe I have a picture of some of these, some of this ferrihydrite crystals. And goethite. And then this is ferrihydrite as this actually is precipitating. And goethite, kind of neat. So how do we build these? So now it's time to move to crystalline silicate clays. And in order to understand where the net negative charge comes from, we need to really talk about their structure. So we'll try to build these from the ground up, so to speak, molecule by molecule. AKA, so what are the crystalline silicate clays? We've called them another term. What have we called these crystalline silicate clays just a few slides ago? Phyllosilicates. Okay, we're talking about phyllosilicates that we're building, crystalline silicate clays. Ooh, here's a question. We've talked a little bit about soil orders, and we talked about spotosol and so forth. What of these orders, which orders do not have silicate clays? Which orders are missing phyllosilicates? And think for a minute. And last week we visited some of these orders, if you remember, one in particular. So how about, let's ask the question a different way. What intense weathering environments exist? What are processes? Remember the process of laterization? Okay. So what soil order is associated with laterization? Do you remember that? What soil order is associated with the process of laterization? This intense leaching, silica removed from the profile. We talked about tropical and subtropical, high energy, high temperature, high rainfall. That would be the oxisols. Okay. How about volcanic environments? We talked a little bit about soils of volcanic regions, the andisols. So we've talked about these. So the andisols, the oxisols, and the soil order we were in last week, the histosols, the organic soils, they really don't have much in the way of crystalline silicate clays. Let me kind of tie those concepts together. Oh, I was ahead of myself with the organics. Think about the muck farm. Okay, now we're going to go back to those crystalline silicate clays and look at them a little more in detail. And here's an illustration. So this comes from figure 8.1. This is our clay crystal. And we've talked about external surface area. But if you look at this in depth, in detail, these are actually layers and interlayers. There's a lot of internal surface area on this external crystal. And so when we talked about specific surface area being high just due to the external surface, now we're going to look at the internal surface. And you can see for any one of these surfaces, there's a tremendous amount of internal surface for some of these clays. And all those internal surfaces adsorb cations, illustrated here, and allow water in. And now we'll look at the structure of those. So this internal surface area sometimes dwarfs the external surface area. So how do we get these? We have to go back to the building of these. Let's construct our silicate clays, our phyllosilicates. And the basic structural unit for this is the silica tetrahedron. So here is oxygen, and 4 oxygens in this pyramid shape. Voila. Silicon in the middle. This is covalently bond. This is the silica tetrahedron, the basic building block, one of the basic building blocks for the silicate clays. The other one is the aluminum octahedron. Okay, it's an 8-sided ring. Now it's an 8-sided figure. 6 oxygens coordinate around 1 aluminum or a magnesium. Okay? So these are the 2 building blocks. We can put these together and make silicate clays. These are the basic building blocks. Silica tetrahedron, alumina octahedron. Aluminum covalently bonded with 6 of these OHs, and silica with 4 of these O's and OHs. Oh, quiz time. Question to review: what is the source of the net negative charge for the organic colloids? And I'm asking you this because I want you to differentiate this from the inorganic or the silicate clays. So that's my purpose. We're going to bring this up and remember this. Because the next question, what's the source of the net negative charge for phyllosilicates, has a different answer. So what's the answer for number 1? What is the source of the net negative charge for the organic colloids? And the answer is dissociation of hydrogen. Okay? And that was from those 3 groups: carboxyl, phenyl hydroxy, and alcohol hydroxy. Okay? Now it's very different for the phyllosilicates, and we go on. Here we go. Watch out for those phyllosilicates. Whoa. Here's the building block. We take these silica tetrahedron and we start to put them together and change. You'll notice 1 tetrahedron in this stick model joined to the next one. So we can continue to go and we can build sheets. So this would be a silicon tetrahedral sheet. Covalently bond these and share the oxygens with each of the adjacent units. And we could do this with a model and build a nice long sheet and lay it out on the table. Okay? That would be a silica tetrahedral sheet. We can take the aluminum octahedron, the aluminums with the 6 covalently bonded oxygens, and we can start stringing those together covalently. And thus we build an aluminum octahedral sheet. And so now we come back to this diagram here, this crystalline silicate clay, and look at these individual sheets. We have silica, all of these individual sheets, silica sheets, and now we can see where that internal surface comes from. Okay. So we can represent that with a rectangle. Rather than draw this each time in our mind, we can fix, here's our silica sheet, silica tetrahedral, and we can represent that by this rectangle, a tetrahedral sheet. We can build the octahedral sheet and connect that to the tetrahedral sheet and represent that whole ball and stick model by a rectangle. So here's a tetrahedral sheet and an octahedral sheet. And we can keep going. So here's a layer, a tetrahedral sheet, an octahedral sheet, a tetrahedral sheet, and we're going to call this a layer. Okay? And it's going to represent this ball and stick model. Okay, well, that's a lot of information. Okay? So I'm going to pause for a minute. Actually, I'm going to pause for a lot of minutes until our next lecture and kind of review what we've done. Okay? We've looked at the colloids. We've classified them into types, organic and mineral. We then looked at the organic colloids and how they were built, and looked at the carboxyl groups, the phenol hydroxy groups, and the alcohol hydroxy groups. And that led us to an understanding of the source of net negative charge. And then we put all those together in these big molecules and showed association and dissociation of hydrogen replaced by cations. We then went to the mineral soil colloids and looked at the phyllosilicates and then the non-crystalline. And so a little bit different structure. Now we're not dealing with CH and O. Now we're dealing with silicon and aluminum. And we started to put those together, and we build layers and sheets, and putting silica layers and tetrahedral aluminum octahedral layers together. And so that's where we're at. And so now we have a basis to understand the source of net negative charge. And so that's where we'll pick up on tomorrow's lecture. So this has been quite a bit to take in. So review this. It's all explained in the text and things that are fuzzy. And we'll be visiting this topic again on Monday, as well as in the lab next week. So when you come to lab, make sure you bring this material, make sure you bring your calculator, and make sure you've read up on this, because the chemistry lab is perhaps one of the more complex ones in terms of understanding. And so with that, I bid you a good afternoon, and by the time I see you again, I'll be coming back from Long Beach, and we'll have a nice set of lectures and labs next week. And have a great day, and I'm signing off.